Hello everyone, we're nearly halfway through. According to my original schedule, you should be starting this module no later than by the beginning of week 7. And then in week 8, we're going to have the midterm exam. Up until now, I've been covering Calculus 2 materials pretty much according to our textbook. I've been following the textbook's order pretty much faithfully. However, from this point on, I'm going to make a radical departure as far as the ordering is concerned. I'm going to skip Chapter 8 and Chapter 9 and we'll go directly to Chapter 10. There's a reason for that. Chapter 9, Differential Equations, will be covered by separate course or separate courses based upon how you do it. Maths 3410 and 3420 differential equations 1 and 2 exist for that reason, so it's going to be pointless for me to talk about it in this course. And Chapter 8, further applications of the integration, is rather problematic. It's a kind of jumble of different types of applications. First two sections are actually embedded inside Chapter 10. 10.2 to be more precise, and the other three sections are all applications outside mathematics. And considering the kind of composition we have in our math courses in University of North Texas Dallas, it's kind of pointless going over these kind of things, so Chapter 8 is completely out. And let's talk about Chapter 10. But before that, some review. As a matter of fact, I usually cover parametric curves and their calculus in Calculus 1, Math 1710D. And if you remember all these topics, then that's good. But for the student who haven't done those kind of things, and let's go over those again. Now, what is a parametric curve? It's a kind of curve given by a pair of two functions. X is given by a function of t, y is given by a function of t, where t is between a and b. We can understand parametric curves as a trace of a moving particle, where t is time and x and y are horizontal and vertical component of the position, kind of like this example shows. X is given as cosine of t plus sine of 3t, y is given as sine of t plus cosine of 3t, as in this example, and t is running from 0 to 2 pi, and as t moves on from 0 to 2 pi, and you're gonna get this kind of motion because x of t and y of t give you at the horizontal and vertical position of this motion, and x and y are both periodic functions with periods 2 pi, not consequently, as t moves from 0 to 2 pi, we have to get back to the original place. Consequently, we get a closed curve like this. Next example is not going to be a closed curve, and we get something like this, and this looks like a graph of a function, except that it has moving particle model. And it's so natural because if you look at this parametric curve, we have x is equal to t. And consequently, plugging in x equal to t to the second equation here, I get y equals a function of x times sine of x squared. Consequently, we get a graph of a function. And this example is actually a justification why we are skipping Chapter 8. There's no reason to talk about graph of a functions in a separate chapter and do this all over again for parametric curve. Parametric curve is more general. All you have to do is plug in x equal to t, and then that's it. There's no reason to study graph of a function separately, memorize formulae separately, and so on and so forth. Third example, here it is. This is an example where x and y are given by definite integrals. And what we have is something like this. Oh, let's slow down this motion a little bit. We have a repeller in the third quadrant and an attractor in the first quadrant. And my point is repelled away slowly. Actually, not radially slowly, but in terms of rotation, very quickly moves. And follow this path and then attracted into the attractor in the first quadrant. Interesting picture we have. By the way, this function x is given as integral 0 to t cosine of s squared ds, and then similar sine of s squared ds. These functions are called Fresnel functions, named after French 19th century French mathematician, physicist, engineer, and entrepreneur Fresnel. And he invented Fresnel prism, and he made a lot of money from those optics, creating some lenses, and the mathematical background of all those are related to these Fresnel functions. It's kind of amazing story. Okay, some more examples. Let's talk about polar curves. Now, if you remember what is a polar curve and polar coordinate from pre-calculus or trigonometry course, Math 1650 or Math 1600, great. If you don't, just regard polar curves as some kind of special case of parametric curve where x is given by r times cosine of t, y is given by r times sine of t. R is given by a function like this, 1 plus 2 sine of t. Traditionally we use theta, but if you look at it in terms of time t, then it's going to be t. And x is r times cosine of t, so like this, parameterized. Y is r times sine of t, so we have that function. So we have a parametric curve. And moving particle model kind of looks like this. By the way, this curve is called Lemasson. Polar curves always move counterclockwise because t is equals to theta, and the angle increases in counterclock direction. Next curve. This is a curve I took from old textbook. Stewart's textbook, maybe 4th edition or 5th edition or something like that. New edition doesn't have this one for some strange reason. I like to call it a flower because for some reason this trace of moving particle, this parametric curve, reminds me of a flower. It looks like a flower. It's almost as beautiful as a flower. By the way, in this curve we have denominator 2 inside sine function, so the period is not 2 pi, it is 4 pi. And then this example is something I made up, and I named it butterfly for an apparent reason, for an obvious reason. Again, period is 4 pi because of the denominator 2. This addition is no big deal. This one is a big deal. Okay, those were examples of parametric curves and the moving particle model. And let's talk about basic calculus. Every semester I taught Calculus 1, I included tangency problems of parametric curves. And step-by-step procedure is kind of like this. Given parametric curve and given t value, t equals to t naught, you can find out x naught, y naught by simply plugging in t equals to t0 to the original parametric curve. For example, if you have parametric curve kind of like, like this one, d, for example, plug in pi over 2 to this t here and there, and then you're going to get x naught value. Plug in pi over 2, pi over 6 the t naught value to here and there, then you're going to get y naught value. That's how you get a point. If you have a point and a slope, then you can find out an equation of the tangent line by slope point equation like this. Y equals m times x minus x naught plus y naught. We just found out x naught and y naught by plugging t equal to t0. And if I find out the slope, then you're going to get the slope point equation. If the slope is undefined, then you're going to have a vertical line, x equals to x naught, and that's easy to find out. When you do slope computation, you're going to get denominator 0 or something wacky, and that's how you know you're going to get a vertical line. Now, how do you find out the slope? Slope formula is extremely simple, y prime of t naught over x prime of t naught, and the deviation is kind of like this. Here in this picture, the blue curve segment is a part of a parametric curve, and then red line segment is its secant line. And the secant line has slope, rise over run, delta y over delta x. The difference of y coordinate over difference of x coordinate. You can see that from this right triangle, highlighted in black. And those delta x and delta y, those changes are caused by change of time. Let's say that change is delta t, then okay, let's expand this font a little bit. And you can divide by delta t, both from numerator and denominator, consequently changing nothing. And then what do we do? Take the limit. Then delta t is going down to 0. Consequently, all delta x, delta y, they all go down to 0. So we have 0 over 0 times 0 over 0 type limit. And the result is the derivative, dy dx. And the right hand side is dy dt over dx dt. Precise argument will follow the chain rule. But this kind of picture and rough argument using the finite difference will do just fine. Now we have dy dx is given by dy dt over dx dt. All I have to do is specify t value, specify t equal to t naught, and we get this slope formula there. Y prime of t0 over x prime of t0. So if you do computation, how does it work? Let's stick to example D, and you can calculate x naught, y naught by just directly plugging in. Okay, that was step 1. And then next, we can calculate the derivatives using the chain rule, this one and that one. And then plug in pi over 6, and then use the slope formula. Then you're going to get slope m value, and then you'll have slope intercept equation. Okay, let me open it. Here is the solution. Plugging in x naught, we have this. Plugging in y naught, we have that. Just plug in t equal to pi over 6 and do the computation. Next, take the derivative, x prime and y prime, using the chain rule. Now finally, plug in pi over 6 to the slope formula, y prime over x prime at that value. Do the computation, you get negative 2/3. That's the slope, and then you found out the points already. So plugging everything into the slope point equation, we have an answer. Y equals to negative 2/3, parenthesis open, x minus x naught, which is pi over 3, plus y naught, which is pi over 6. And this is sufficient for the final answer as far as I'm concerned. After all, this is calculus 2, so I trust you are all capable of doing algebraic manipulation. But if you want to really do the algebraic manipulation to get slope-intercept equation, you can go a couple of steps further. By the way, here is the visualization, kind of like that. And you can do the rest of the problems, and I particularly emphasize this problem because you'll have to use fundamental theorem of calculus somewhere. and at some point you may end up getting some vertical lines as well.